Hi, this is Mr. Gettle, and today we're going to talk about work and power. So work is essentially a force applied over a distance, and power is just the time it takes for that work to be done. And so I want us to start by thinking about two boxes hanging from some set point in the ceiling. And one is being pulled up faster by a little motor, and one's being pulled up slower by a little motor. So a question that we might want to ask ourselves is, which one is doing more work? Well, they are both going the same distance and there is the same amount of force needed to do that, so it is the same work. But which one has more power? Well, since the one on the left goes faster, it has more power. So work is just the energy required done on an object or in a system, and power is the time that it takes for that work to be done. So work, the equation for that, as we have learned, is force times distance, or force parallel to the distance moved. And then power is just the work done, or the change in work done over a change in time. And so we use that little delta, the triangle looking thing, as a change. And so I want us to imagine this guy throwing a ball. Now he's moving that ball over a distance, and it requires force for him to do that. So he is doing work. And that ball is moving parallel to the force that he's applying. And so both force and distance need to be parallel to calculate the work. So work is just the force parallel to the distance, and so force times distance. And so let's think about this example. We have a 6.0 Newton object sitting on a table, and we apply a force, but it does not move. So we have 6.0 newtons, and we have 0 meters because it hasn't moved. So we've essentially done 0 joules of work. Now that's different than we would think of in regular life, right? Work would be defined differently. Now imagine we have a 16 Newton force on that object and it moves 2 meters. Well, work again is force times distance, so we have 16 newtons times 2 meters, which is 32 joules. So let's take that example and let's calculate power. And so again, power requires us to know a time or a change in time. So if we have that 16 Newton force on that object, and again it moves 2 meters, we already know the work is 32 joules. And so power is the change in work over the change in time. And so the change in work here is 32 joules. And let's imagine we move that object, the 2 meters, and we do that in 3 seconds. So our change in work again is 32 joules. Our change in time is 3 seconds. So our power is 32 divided by 3. And so roughly around 11 watts of power. Now if we change the time and we make that box move much quicker, 0.5 seconds to get that 2 meters, what's going to happen to our power? Well, our power is going to increase, right? Because we 32 divided by 0.5 seconds, and our power is going to increase all the way up to 64 watts. So much greater power. So if you think about that, we use watts to describe the power of a light bulb. And so how do we measure this in the physics lab? Well, you could do this on a table. You could have your object and maybe have some wheels on it, and you could hook it up to a scale spring. And that spring can measure the force. And you can measure the distance. And if you do that, you can measure the amount of power and work. Well, you can measure the amount of power and work, yep. And so if you want to measure the amount of work using a graph, that's pretty easy as well. You can put force on the y-axis, distance on the x-axis. And if you draw your line for the applied force over that distance, especially if it doesn't change, it will be a straight line across. And really a simple way to calculate that work done is to find the area underneath that line. So that would give you your work. I hope this has been helpful. We'll see you next time.